Chemical calculations is an area that students sometimes they struggle with. I will admit that. Chemical calculations are really, they're unit conversions, and they're very specific sets of unit conversions. When we look at these chemical calculations, we are looking for things such as how much product, or how much reactant. That's typically the question that you're going to have asked. It goes a little bit further, because for me to ask, how many cookies can you make? I don't know, how much flour, how much eggs, and how much sugar do I have? Right? If I say I need, I don't know, I need, gosh, let's see. I need 12 peanut butter sandwiches. How many slices of bread are you going to need? So there's going to be some kind of a relationship between two things. One could be a reactant and one could be a product. It could be something akin to, well, if you have, I don't know why I keep using food examples, but I do. I need tires for 20 cars. How many tires do I need? Those are both reactants, right? I've got two things that I'm going to be putting together to make cars that can go off the assembly line. Chemical calculations are those types of questions. If I have this much reactant, how much of my other reactant do I need? I want to make this much product. How much starting material do I need? I have this much starting material. How much product can I make? These are all these chemical calculation type questions, and they're all going to be based upon what's called the mole ratio. So this mole ratio is what we were developing when we balanced these chemical equations. A mole ratio So it is going to allow us to come up with a mathematical relationship between any two species in a chemical formula or in a balanced chemical equation. I don't really want you to get too hung up on the word mole. Instead, think of it just as a ratio. A mole is sometimes described as a chemist's dozen. And I don't know if I really like that description, but it is the description that is most often used. And so let's think about a dozen, right? 1 dozen eggs. Oh, that's easy, that's 12 eggs. Perfect. Dozen pencils. Fine, that's 12 pencils. Mm-hmm. 1 dozen shirts. It's getting silly. Right. There's 12 shirts. The key thing here, the word dozen goes with 12. A dozen is 12. A dozen is 12. I don't really care. I will be very honest. In this first case, that was about eggs. That's nice. Pencils, whatever. Shirts, yeah, okay. How about 1 dozen helium atoms? Okay, well, that's nothing more than 12 helium atoms. Perfect. So the term dozen just refers to a certain number of whatever you're talking about. So 1 dozen is 12. Okay, good, good. Mole, same idea. 1 mole, let me start over there. Okay. So 1 mole is 6.022 times 10 to the 23rd power. If I have 1 mole of helium atoms, I would have 6.022 times 10 to the 23rd power helium atoms. I could have 1, and the abbreviation for mole, you drop the E. 1 mole of water well, there's 6.022 times 10 to the 23rd power water molecules. I suppose I could. 1 mole of eggs. Yeah, there'd be 6.022 times 10 to the 23rd power eggs. It's a lot of eggs. A lot of eggs. Why do we have this concept of mole? If we step back for a moment and think about collision theory. Collision theory where we had, for example, particle where we had H2, right, and I2 colliding with each other, right? So we have these guys moving this way, moving this away, and they're coming in and they're bashing into each other side by side. Sideswipe, right? The relationship for this reaction is 1 H2 reacts with 1 I2. And then, of course, we get those 2 HIs. Fabulous. The problem is there's no way to physically go pick up a single hydrogen molecule. There is no way to physically go pick up 1 iodine molecule. But this is the reaction. The reaction happens between 1 molecule of H2, 1 molecule of I2. That's the ratio. 1 H2 combines with 1 I2. We understand it on a submicroscopic level, on the particulate or atomic level, as 1 molecule with 1 molecule. But if we want to talk about calculations, if you want to talk about going and doing it in the lab, I most certainly cannot pick up individual hydrogen atoms. I cannot, or molecules, H2 molecules. I can't do the same thing with I2. I need a way to be able to know how many I2 and how many H2 I have in my container when I start to react them. So if I have 10 I2 molecules, how many H2 molecules do I need to put in there to get them to react totally? Well, I need to put 5 in. As I said, individually, these things are way too small. How about if we put together a bunch of them? I don't know, maybe like 6.02 times 10 to the 23rd power. So instead of thinking about this one H2 molecule, instead of thinking about this as just one H2 molecule, instead, I'm going to think about this as a box. And this box is going to have 1 mole of H2. And then I'm going to go ahead and have a secondary box. Again, this is for calculation. And in the second box, I would have 1 mole of I2. So all of a sudden, I've gone from just a single H2 to now having a box. Well, 1 mole of H2 is 6.02 times 10 to the 23rd power. Individual molecules. I have the same thing going on with the I2. When I bring them together for my product, I'm going to need a bigger box because now I have 2 moles of HI. Let's think about this in terms of a dozen, okay? Let's get rid of this mole idea for a moment. Well, no, that's not. So let's see. I've got H, come here, H, 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 1, 2, 3, 4, H, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh my goodness. 12. Okay. Yes, I wrote down 12 of them. Guess what? I'm going to do the same thing with the I2s. Got I, I2, I2, I2. Whoops. Let's try that again. Ag. I'm already starting to try to write the product. In other words, I've got I2, right? This is H2. So I'm going to bring them together. H2 plus I2 going to give me 2 HIs. Same thing the next line, 2 HIs. Same thing. And so on, and so on, and so on. One, 2, 3, 4, 5, 6, 7. Okay. That's awesome, right? So if I look at just this top line, 1 H2 plus 1 I2 gave me 2 HIs, correct? That big ugly box. That's 12, right? So I have 12 H2s. Same box here. It's 12 I2s. And here, there's 24 HIs. Well, 12, that's just a dozen, right? Yeah, it's a dozen. So I've got, instead of 12 H2s, I could write 1 dozen H2 and 1, I don't know, dozen seems a little bit long to write. I'm gonna call it DZ, and 1 dozen I2s. And what does that give me? It gives me 2 dozen HIs. One, 2. 1, 2. The ratio on the atomic molecular level of 1 H2 plus 1 I2 giving you 2 HIs. That ratio is what's important with the reaction. It's 1 plus 1 gives me 2 products. Now all of a sudden I have 1 dozen H2, 1 dozen I2, and get 2 dozen HI. It's still 1 H2, 1 I2, and 2 HI. That ratio is still there. I could be talking about that individual box, okay, of one molecule, making my 2 molecules of HI. Or there's a box where I've written 12 of them down, 1 dozen. Then the box where I wrote another 12 of them down, another dozen. And here's the big box at the end where there are 24 of these individual HI molecules. 2 dozen. It still holds. Okay, that ratio still works. Whether we're talking about individual molecules and atoms, an individual to make my product, or if I'm talking about 12 of them, plus 12 of them, gives me my 24. It's still 1 H2, 1 I2, 2 HI. That's why, in terms of chemistry, my boxes are just a lot bigger, a lot bigger. 1 mole of H2 and 1 mole of I2 gives me 2 moles of HI. A mole is nothing more than the name that we give to a box of atoms or a box of molecules. That box just contains a certain number of, in this case, H2 molecules, I2 molecules, and then 2 moles of HI. As I said, one of the reasons why we went to moles is because we can't actually go and pick up individual pieces. And this is where the idea of molar mass comes into play. Okay, let's see. I don't know, do I want to give the really smarty pants comment? I think I do. No, I don't. Okay, molar mass. It's the mass in grams of 1 mole of a substance. Molar mass, numerically, the same as an atomic mass. The reason why molar mass and atomic mass or formula masses are the same numerically is based upon the definition of a mole and the definition of an atomic mass unit. one, come on. Let's see. One, oh my gosh, let's see here. Oh, one neon atom. According to my periodic table, is 20.1. I don't like this periodic table. Okay. 1.8. Okay. We use this fancy atomic mass unit. That's really nice. If I give you a box of neon atoms, 1 mole of neon, it's going to have a mass of 20.18 grams. And it goes for everything across the board, across the periodic table. 1 carbon atom has an average mass of 12.01 AMU. 1 mole of carbon is 12.01 grams. When your text goes through and starts talking to you about how to calculate formula masses and average formula mass and such, don't worry about it. We're going to go straight for the jugular, meaning we're going to go straight for these molar masses. I want you to understand that when we talk about a mole of a substance, we are talking about a lot of individual pieces. These individual atoms, individual molecules are so incredibly small that we need a way to count out how many individual pieces there are with using something that we can measure. And that's where the molar mass comes into play. So molar mass of an element is from your periodic table. I don't know why I'm doing that. If we're going to find a molar mass of some compound or some substance, it's simply the sum of the molar masses, molar. Swear this is my last piece. Excuse me. Okay, so now let's break this down a little bit, because this is really, you've done all of this before. This is just adding one little piece to interpretation of a chemical formula. Let's take H2O and balanced chemical equations. How many hydrogens? There are 2. Okay, huh? Yep. How many oxygens? There's 1. Yep. In one water, there are 2 hydrogens and 1 oxygen. Remember that ratio of the boxes and the dozens and such? If I had 1 dozen water, how many hydrogens would there be? There'd be 2 dozen. There'd be 1 dozen oxygens. So if I have 1 mole of water, there's going to be 2 moles of hydrogen and 1 mole of oxygen. Thus, if I want to calculate the molar mass of water, I would have 2 times the molar mass of hydrogen plus 1 times the molar mass of oxygen. Hydrogen is 1.01 grams per mole. Oxygen is 16.00 grams per mole. Together, it would be 18.02 grams per mole. Water is the molar mass of water. In other words, 1 mole of water has a mass of 18.02 grams of water.